This lecture introduces Chapter 23. In Chapter 22, we learned how the electric field is defined. In this chapter, you will learn how to calculate and use the electric field. Four common electric field models are the basis for our understanding a wide variety of electric phenomena. The first two are a point charge and an infinitely long line of charge. We will develop the electric fields for these later. The next two electric fields are the electric field due to an infinite plane of charge and a charged sphere. The electric field of a point charge is Coulomb's law for an electric field that was introduced in Chapter 22. The electric field is a vector and points away from a positive charge and towards a negative charge. The electric field is defined as the force on a positive test charge due to the distribution of source charges. The test charge does not change the shape of the electric field. The SI units of electric field are therefore newtons per coulomb. The table gives the electric field for common phenomena. The electric field due to a distribution of charges is the vector sum of the electric fields due to each charge. In other words, electric fields obey the principle of superposition. What is the direction of the electric field at the dot? The test charge is always a positive test charge. The positive charge produces an electric field up and to the right. The negative charge produces a field down and to the right. The sum of the two vectors is to the right. The problem-solving strategy for multiple point charges is model the charged objects as point charges. Establish a coordinate system and show the locations of the charges. Identify the point P at which you want to calculate the electric field. Draw the electric field of each charge at P. Use symmetry to determine if any components of the electric field are zero. The representation of the net electric field is the vector sum of the electric field for each individual point charge. For each charge, determine its distance from P and the angle of the electric field from the axis. Calculate the field strength of each charge's electric field. Write each electric field vector in component form. Sum the vector components to determine the net electric field. What is the direction of the electric field at the dot? Since the test charge is always positive, the direction of the electric field due to the positive charge points to the right. The electric field to the negative charge points to the left. Since the negative charge is closer to the evaluation point than the positive charge, the strength of the electric field due to the negative charge is greater than the positive charge. The net field must point to the left. When R is much greater than D, the electric field strength at the dot is This problem is similar to example 23.1 in the book. By symmetry, the y components of the electric field cancel, leaving a vector that points to the right. The magnitude of the electric field is equal to 4 times q divided by 4 pi epsilon naught r squared. The 2 comes from a charge of 2q at the origin. The electric field at a far distance from the set of charges is equivalent to a point charge of charge 4q. An electric dipole is two equal but opposite charges separated by a small distance. A water molecule is a permanent dipole. The oxygen atom has a larger positive charge than the two hydrogen atoms, and the electrons spend more time in the vicinity of the oxygen atom. The dipole on the right is an induced dipole created by the electric field, stretching the shape of the charges, with more positive charge at one end and more negative charge at the other. Since the electric field repels positive charge, the positive charge of the dipole is always away from the source charge. It is useful to define the dipole moment P, shown in the figure, as the vector qs from the negative to the positive charge. The SI units of the dipole moment are Coulomb meter. To see where this comes from, consider two charges of equal but opposite charge Q. The net electric field is the vector sum of the electric field to the positive and negative charges. Using Coulomb's law, the net field is shown. The binomial expansion tells us how to write the sum of two numbers raised to a power in terms of the sum of various powers of a plus b. If a is 1 and b is x, the binomial expansion may be written as 1 plus n times x to the first order. Factor out x squared and use the binomial expansion yields 2 qs divided by 4 pi epsilon naught x cubed. We define the dipole moment based on the results of the previous slide as the vector qs from the negative to the positive charge. We will now calculate the electric field from a dipole at two specific points, one on the line connecting the two charges, the other along the line bisecting the dipole. At the point on the axis of the dipole, above the dipole, the electric field is given by the superposition of fields from the two charges separated by the distance s. Factoring out y squared and using the binomial expansion yields 2qs divided by 4 pi epsilon naught y cubed, where we recognize that qs is the dipole moment. We substitute the distance from the center of the dipole r for y and get 2p divided by 4 pi epsilon naught r cubed. At the point bisecting the dipole, on the right, the magnitude of the electric field for either charge, both the distance d away, is given by Coulomb's law. Q divided by 4 pi epsilon naught d squared. The two vectors are shown in the diagram. From symmetry arguments, we see the electric field in the x direction for the positive charge is to the right, and the electric field to the negative charge is to the left. Since the distances are the same for the two charges, the sum of these two fields must be 0. The y component of the fields from the two charges are in the same direction, the minus y direction. Only the component of the fields along the y-axis contributes to the field, and this is the sine of the angle. Since the sine of the angle is half the distance between the charges divided by the distance, the electric field can be written as minus qs divided by 4 pi epsilon naught d cubed. The Pythagorean theorem gives us the distance in terms of x and s. Since x is much greater than s, d is approximately the distance along the x-axis. As a general statement, we replace the distance x by the distance from the center of the dipole r. We then have the electric field of a dipole on the axis of the dipole and in a plane bisecting and perpendicular to the dipole. The bisecting field is opposite to the dipole direction and is only half the strength of the on-axis field at the same distance. The water molecule H2O has a permanent dipole moment of magnitude 6.2 times 10 to the minus 30 coulomb meters. What is the electric field strength 1 nanometer from the water molecule at a point on the dipole's axis? Since R is much greater than S, and we can use the on-axis electric field of the molecule's dipole moment, this gives a field strength of 1.1 times 10 to the 8 newtons per coulomb. The concept of electric field lines was introduced by Michael Faraday, which helped him to easily visualize the electric field using intuition rather than mathematical analysis. Electric charges create an electric field in the space surrounding them. The electric field lines act as a kind of map that gives the direction of and indicates the strength of the electric field at various regions in space. Electric field lines are continuous curves tangent to the electric field vectors. Closely spaced field lines indicate a greater field strength. Electric field lines start on positive charges and end on negative charges. Electric field lines never cross. The figure shows the electric field lines of a positive point charge and a negative point charge. They are radially directed towards or away from the source charge. Two protons, A and B, are in an electric field. Which proton has the larger acceleration? The answer is A. The closer field lines show where the electric field and the electric force is stronger. An electron is in the plane that bisects the dipole. What is the direction of the electric force on the electron? This is the dipole with the dipole moment pointing up. The electron is at a point that bisects and is perpendicular to the electric dipole. The answer is A. The electric field vectors are tangent to the electric field lines. Since the dipole points up, a positive test charge would feel a force pointing down. Since the electron has a negative charge, we simply reverse the direction of the force, and the electric force must point up. An electric dipole is formed from plus and minus 1 nanocoulomb charges spaced 2 millimeters apart. The dipole is at the origin, oriented along the x-axis. What is the electric field strength at points 10 centimeters, 0 centimeters, and 0 centimeters, 10 centimeters? The distances to the observation points are large compared to the size of the dipole, so model the field as that of a dipole moment. The dipole moment points from the negative to the positive charge. The dipole consists of charges plus and minus q along the x-axis. The electric field for point A points to the right. The dipole moment is 2 times 10 to the minus 12 coulomb meters to the right. The electric field at 10 centimeters, 0 centimeters, which is at a distance of 0.1 meters, is at a point on the axis of the dipole. It must be 36 newtons per coulomb and point in the same direction as the dipole moment, or to the right. Since the problem only asks for the electric field strength, the answer is 36 newtons per coulomb. The dipole consists of charges plus and minus q along the x-axis. The electric field for point B is a point that bisects the dipole and must point to the left. The dipole moment is 2 times 10 to the minus 12 coulomb meters to the right, the same as in part A. The electric field at 0 centimeters, 10 centimeters, which is at a distance of 0.1 meters, is in a plane perpendicular to the electric dipole, and is 18 newtons per coulomb to the left. The field strength then is 18 newtons per coulomb. The linear charge density of an object of length L and charge Q is defined as the total charge on the object divided by the object's length. Linear charge density has units of coulombs per meter, is the amount of charge per meter of length. If 8 nanocoulombs of charge are placed on the square loop of wire, the linear charge density will be The answer is C, 200 nanocoulombs per meter. There are 4 lengths of wire, each 1 centimeter long. The surface charge density of a two-dimensional distribution of charge across a surface area A is defined as the total charge of the object divided by the object's surface area. Surface charge density, with units of coulombs per square meter, is the amount of charge per square meter. A flat circular ring is made from a very thin sheet of metal. Charge Q is uniformly distributed over the ring. Assume W is much, much less than R. The surface charge density eta is then The ring has 2 sides, the top and bottom surfaces. If the width is very small, the inner circumference is identical to the outer circumference, and the surface is a rectangle of width equal to W and length equal to the circumference. So A is 2 times the length times the width, or 4 pi RW. The answer is B. Integration is summation. An integral is a sophisticated way to add an infinite number of infinitesimally small pieces. The area under the curve happens to be a special case in which you're summing small areas. Suppose we want to find the total charge of a thin charge rod of length L. First, we establish an x-axis with the origin at one end of the rod. Then we divide the rod into tiny segments of length dx. Each of these little segments has a charge dq, and the total charge on the rod is the sum of all the values dq. Now the critical step. The rod has some linear charge density, lambda. Consequently, the charge of a small segment of the rod is dq is lambda dx. The total charge on the object is found by summing all the small charges. If we now let delta qi go to 0 and n go to infinity, we define the total charge as the integral over the object for all charge elements dq. For a rod of length L and linear charge density lambda, the object is the rod, so the integral is the one-dimensional integral over the length of the rod. To find the electric field of a continuous distribution of charge, model the charge distribution as a simple shape. For the pictorial representation, draw a picture, establish a coordinate system, and identify the point P at which you want to calculate the electric field. Divide a total charge Q into small pieces of charge delta Q, using shapes for which you already know how to determine the electric field vector. This is often, but not always, a division into point charges. Draw the electric field vector at P for one or two small pieces of charge. The net electric field is the superposition of the individual electric fields. We write an algebraic expression for each of the three components of the electric field vector, unless you are sure one or more is zero at point P. Let the x, y, z coordinates of the point remain variables. Replace the small charge delta q with an equivalent expression involving a charge density and a coordinate such as dx. This is the critical step in making the transition from a sum to an integral because you need the coordinate to serve as the integration variable. Express all angles and distances in terms of the coordinates. Let the sum become an integral. The integration limits for the variable must cover the entire charged object. Example 23.3 in the text uses integration to find the electric field strength at a radial distance r in the plane that bisects a rod of length L with total charge Q. We can use symmetry arguments instead of direct calculations. Consider two elements of charge delta Q, one at the top and one near the bottom. Only the top charge is shown. The magnitude of the electric fields for these two charges is given by Coulomb's law. We let the distance from the top and bottom to the point be the same and equal to r sub I. The y component of the charge at the top must point down, and the y component of the charge at the bottom must point up. From symmetry, the total field strength in the y direction must sum to 0. To calculate the x component of the field, consider a single element I of charge, delta Q, that produces an electric field in the x direction as shown. From trigonometric identities, we can find r sub I and the cosine of theta. We can define the linear charge density and then the charge element delta Q. The incremental electric field is shown. The total field in the x direction is the integral sum of all elements over the length of the rod. The direction of the field is radially away a positively charged rod. For a negatively charged rod, the electric field points toward the rod. As shown by the calculation on the right-hand side, the charge element is lambda dx, where lambda is q divided by L. From the Pythagorean theorem, the distance is the square root of x squared plus y squared. The y component of the electric field is the magnitude of E times the cosine of theta. The magnitude of E is from Coulomb's law, and the cosine of theta is y over r, or y over the square root of x squared plus y squared. Combining these yields the correct answer of D. Using Q equal lambda L, the electric field of a rod of charge may be rewritten in terms of the linear charge density. If we now let L go to infinity, the last term becomes simply 1, and we're left with 2 times lambda divided by 4 pi epsilon naught r. Notice the dependency is 1 over r. The direction of the field is away from a line of positive charge and toward the line of negative charge. The electric field 5 centimeters from a very long charge wire is 2,000 newtons per coulomb toward the wire. What is the charge in newtons per coulomb on a 1 centimeter long segment of the wire? Assume that the wire is thin and that the charge lies on the wire along a line, then use the electric field due to a line of charge, where r is the distance from the line in the plane that bisects the line. Solving for the linear charge density gives 5.56 times 10 to the minus 9 coulomb per meter. The charge on a 1 centimeter segment of wire is 0.056 nanocoulombs. Because the electric field is directed toward the line, Q must be negative. Consider the on-axis electric field on a positively charged ring of radius r. Define the z-axis to be the axis of the ring. The electric field on the z-axis points away from the center of the ring, increasing in strength until reaching a maximum when z is approximately equal to r, and then begins to decrease. To see this, draw a coordinate system where the z-axis is perpendicular to the center of the ring. From symmetry, the field perpendicular to the axis cancels out. Only the z component remains. To calculate the electric field due to a ring of charge, divide the ring into I charge segments, delta Q, at a distance r sub I from the point of interest. The electric field is the field of a point charge, is from Coulomb's law. The component of the field in the z direction is the cosine of the total field due to element delta Q. The usual trigonometric identities apply. The field from a single element I on the ring is shown. To get the total field, we must sum over all elements I. Since neither z nor r are dependent on I, the electric field at a point on the line from the center of the ring is the total charge on the ring divided by 4 pi epsilon naught times z over z squared plus r squared to the 3/2. To find the on-axis electric field from a positively charged disk of radius r, first define the z-axis to be the axis of the disk. The electric field on the z-axis points away from the center of the disk. A disk is made up of rings of charge. One elemental ring of charge produces a field, 1 over 4 pi epsilon naught, z over z squared plus r sub I squared to the 3/2 times delta Q. The area of each ring is the circumference times the thickness. The ring is considered infinitesimally thin. We can define the electric field in terms of the surface charge density, eta. Summing over all elements, and then taking the limit as delta r goes to 0 yields the integral. Which is solved by substitution. Which yields the field produced by a disk of charge. The electric field on the z-axis points away from the center of the disk with magnitude shown. A 10 centimeter diameter plastic disc is charged uniformly with an extra 10 to the 11 electrons. What is the electric field 1 millimeter above the surface at a point near the center? Model the plastic disc as a uniformly charged disc. We are seeking the on-axis electric field. Because the charge is negative, the field will point toward the disc. The total charge on the disk is minus 1.6 times 10 to the minus 8 coulombs. Since the area of the disk is known, the surface charge density can be found. The total electric field is 1.1 times 10 to the 5 newtons per coulomb, directed toward the disk since the charge is negative. The electric field of a plane of charge is found from an on-axis field of a charged disk by letting the radius go to infinity. The electric field of an infinite plane of charge with surface charge density eta is constant. It does not depend on distance from the plane. For a positively charged plane with eta greater than 0, the electric field points away from the plane on both sides of the plane. For a negatively charged plane with eta less than 0, the electric field points toward the plane on both sides of the plane. The direction of the field is away from a plane of positive charge and toward a plane of negative charge. Two protons, A and B, are next to an infinite plane of positive charge. Proton B is twice as far from the plane as proton A. Which proton has the larger acceleration? The answer is C. Since the electric field from the plane is independent of distance, both have the same acceleration. A sphere of charge Q and radius r, be it a uniformly charged sphere or just a spherical shell, has an electric field outside the sphere that is exactly the same as that of a point charge Q, located at the center of the sphere. But this is only for points outside the sphere. We will address inside the sphere in a later chapter. Two 2 centimeter diameter insulating spheres have a 6 centimeter space between them. One sphere is charged to 10 nanocoulombs, the other to minus 15 nanocoulombs. What is the electric field strength at the midpoint between the two spheres? An insulating sphere of charge Q and radius r has an electric field outside the sphere that is exactly the same as that of a point charge Q located at the center of the sphere. Draw a picture of the charge distribution. The charge due to a single sphere is 1 over r squared field. Calculate the magnitude of the fields due to the two individual spheres. For a positive test charge, the two fields point in the same direction, to the right. The figure shows two electrodes, one with a charge plus Q and one with another charge minus Q, placed face to face a distance d apart. This arrangement of two electrodes charged equally but oppositely is called a parallel plate capacitor. Capacitors play important roles in many electric circuits. The figure shows two capacitor plates seen from the side. We use the law of superposition and the fact that the field due to the plane of charge does not depend on distance. Because the opposite charges attract, all of the charge is on the inner surfaces of the two plates. Inside the capacitor, the net field points toward the negative plate. Outside the capacitor, the net field is 0. The electric field of a capacitor is the total charge on one plate of the capacitor divided by epsilon naught and the area of the plate between the plates. The direction of the field is from the positive to the negative plate. Outside the two plates, the field is identically equal to 0 everywhere. 3 points inside a parallel plate capacitor are marked. Which is true? The answer is C. The field between two plates is independent of distance. Outside a real capacitor and near its edges, the electric field is affected by a complicated but weak fringe field. We keep things simple by always assuming the plates are very close together and using the field strength as eta over epsilon naught for the magnitude of the field inside a parallel plate capacitor. Two 1 centimeter by 2 centimeter rectangular electrodes are 1 millimeter apart. What charge must be placed on each electrode to create a uniform electric field strength of 2 times 10 to the 6 newtons per coulomb? How many electrons must be moved from one electrode to the other to accomplish this? The electrodes can be modeled as an ideal parallel plate capacitor because the spacing between them is much smaller than their lateral dimensions. The electric field strength inside the capacitor is Q over epsilon naught A. Thus, the charge to produce a field strength of 2 times 10 to the 6 newtons per coulomb must be 3.5 nanocoulombs. This yields 2.2 times 10 to the 10 electrons. The plate spacing does not enter the result as long as the spacing is much smaller than the plate dimensions. As is true in this example, the field is independent of the spacing. The figure shows an electric field that is the same in strength and direction at every point in the region of space. This is called a uniform electric field. The easiest way to produce a uniform electric field is with a parallel plate capacitor. Air breaks down when the electric field strength reaches 3 times 10 to the 6 newtons per coulomb, causing a spark. A parallel plate capacitor is made of two 4 centimeter by 4 centimeter electrodes. How many electrons must be transferred from one electrode to the other to create a spark between the electrodes? The electric field is a region of space between the plates of a parallel plate capacitor and is uniform. The electric field inside a capacitor is Q over epsilon A. Thus, the charge needed to produce the required electric field strength is 42 nanocoulombs. Dividing the charge of an electron, the total number of electrons is 2.7 times 10 to the 11. Consider a particle of charge Q and mass m at a point where an electric field E has been produced by other charges, the source charges. The electric field exerts a force, Q times E, in the direction of the field due to a positive charge and opposite the direction of the field on a negative charge. The electric field exerts a force, F on Q, equal to Q times E. If this is the only force acting on Q, it causes the charged particle to accelerate with an acceleration equal to the electric force divided by the mass. If the electric field is uniform, the acceleration is constant. DNA fingerprints are measured with the technique of gel electrophoresis. A solution of negatively charged DNA fragments migrate through the gel when placed in a uniform electric field. Because the gel exerts a drag force, the fragments move at terminal speed inversely proportional to their size. A proton is moving to the right in a vertical electric field. A very short time later, the proton's velocity is the answer is C. The acceleration is in the direction of the electric field. The horizontal velocity must remain the same since there is not a force acting in the horizontal direction. Which electric field is responsible for the proton's trajectory? The answer is C. Like gravitational field, the charge follows a parabolic trajectory in a uniform electric field. An electron traveling parallel to a uniform electric field increases its speed from 2 times 10 to the 7 meters per second to 4 times 10 to the 7 meters per second, or a distance of 1.2 centimeters. What is the electric field strength? A uniform electric field causes a charge to undergo constant acceleration. Kinematics yields the acceleration of the electron, 5 times 10 to the 16 meters per second squared. The magnitude of the electric field required to obtain this acceleration is 2.8 times 10 to the 5 newtons per coulomb. The figure shows an electric dipole placed in a uniform external electric field. The net force on the dipole is 0. The electric field exerts a torque on the dipole that causes it to rotate. The figure shows an electric dipole placed in a uniform external electric field. The torque causes the dipole to rotate until it is aligned with the electric field as shown. Notice that the positive end of the dipole is in the direction in which E points. Which dipole experiences no net force in the electric field? The answer is E. None of the dipoles experience a net force. Only C experiences no net torque, while the net force on all three is 0. Only in C are the forces directed away from the same point. The torque on a dipole placed in a uniform electric field is the force times the moment arm. Since the two charges have the same magnitude, the magnitude of the forces is the same on each charge. The total torque is twice the torque on one charge and is equal to QSE times the sine of the angle, or the dipole moment times the electric field times the sine of the angle. Two 1-gram balls are connected by a 2-centimeter-long insulating rod of negligible mass. One ball has a charge of plus 10 nanocoulombs, the other charge of minus 10 nanocoulombs. The rod is held in a 1 times 10 to the 4 Newton per Coulomb uniform electric field at an angle of 30 degrees with respect to the field, then released. What is the initial angular acceleration? The two oppositely charged balls form an electric dipole. The electric field exerts a torque on the dipole, causing an angular acceleration. The figure shows the dipole in the electric field. The dipole moment is 2 times 10 to the minus 10 coulomb meters. The torque is 1 times 10 to the minus 6 Newton meters. The angular acceleration is the torque divided by the moment of inertia of the system. The system is two masses, each a distance s over 2 from the center of mass. The moment of inertia is 2 times 10 to the minus 7 kilogram meter squared, which gives an angular acceleration of 5 radians per second squared. This value of alpha is the initial angular acceleration, when the rod is first released. The torque and the angular acceleration will decrease as the rod rotates toward alignment with the electric field. A dipole near a negative point charge is also attracted toward the point charge. The net force on the dipole is toward the direction of the strongest field. Because field strength increases as you get closer to a finite-sized charged object, we can conclude that the dipole will experience a net force towards any charged object. The water molecule H2O has a permanent dipole moment of magnitude 6.2 times 10 to the minus 30 coulomb meters. A water molecule is located 10 nanometers from a sodium ion in a saltwater solution. What force does the ion exert on the water molecule? The sodium ion has a charge of plus E. The electric field of the ion aligns the water's dipole moment and exerts a net force on it. We could calculate the net force on the dipole as the small difference between the attractive force on its negative end and the repulsive force on its positive end. Alternatively, we know from Newton's third law that the force on the dipole on the ion has the same magnitude as the force of the ion on the dipole. An ion of charge Q equal E will experience a force of magnitude Q E times the electric field of the dipole when placed in that field. Since the dipole's electric field can be calculated, the force of the dipole on the ion is 1.8 times 10 to the minus 14 newtons. Therefore, the force of the ion on the dipole is 1.8 times 10 to the minus 14 newtons. While 1.8 times 10 to the minus 14 newtons may seem like a very small force, it is 10 to the 11 times larger than the size of the Earth's gravitational force on these atomic particles. Forces such as these cause water molecules to cluster around any ions that are in the solution. This clustering plays an important role in microscopic physics of solutions studied in chemistry and biochemistry. NASA astronauts Stanley Love and Donald Pettit and NASA researcher Scott Messenger used the International Space Station's microgravity environment to run experiments on clumping of solid particles. The results have interesting relevance to the studies of how aggregates formed in the solar nebula and the ultimate growth of asteroids and planets. In every trial using salt, sugar, and coffee, the majority of particles clump spontaneously after a few seconds of thorough shaking. The informal experiments described by Love, Pettit, and Messenger support the electrostatic model for particle aggregation in the solar nebula and serves as a springboard for more sophisticated future investigations of the aggregate behavior of millimeter and sub-millimeter sized particles in microgravity. A point charge Q is distance r from a dipole consisting of charges plus and minus Q separated by distance s. The dipole is initially oriented so that Q is in the plane bisecting the dipole. Immediately after the dipole is released, what are the magnitude of the force and the magnitude of the torque on the dipole? you can assume R is much, much greater than S. Because R is much, much greater than S, we can use the electric field of the dipole as minus K times the dipole moment over R cubed for the electric field in the plane bisecting the dipole. From Newton's third law, the force of Q on the dipole is equal and opposite to the force of the dipole on Q. You can see from the diagram that the force of the dipole on Q is down and the force of Q on the dipole is up, in the direction of the dipole moment. The magnitude of the dipole field at the position of Q is 1 over R cubed dependence. The magnitude of the force of the dipole on Q is the same as the force of Q on the dipole. The electric field of charge Q exerts a torque on the dipole. The electric field is perpendicular to the dipole, so theta is 90 degrees. The torque is given by 1 over 4 pi epsilon naught, little q, big Q, S over R squared.